right, for our final idea in statistical mechanics, and to complete this module, we're going to have a short segment here where we talk a little bit more about entropy and use some of the things we know about entropy and some ideas we've gotten from statistical mechanics to make one point here. Okay. We've earlier derived a relationship for entropy in terms of the molecular partition function. That's the top line up here, right? So we've got the partition function is in here, that's Q, N is our number of particles. That last term, U minus U0 over T, that's the internal energy divided by the temperature. Right? If we have a monatomic gas, think an ideal gas model, then the internal energy is only from translation, and that means it would be 3/2 NKT would be the U minus U0 part. Divide that by T, and we get 3/2 NK. And so if I take that and put it in for the U minus U0 term, and then if I realize that here I've got this +1 is also multiplied by NK out there, so I can combine those two pieces. And if I do that, I get here, the first piece comes from the NK that's out in front on the top times the natural log of Q over N. I changed Q to Q translational here because since I'm going for a monatomic gas, that means the translational partition function is the only piece that, that matters. Right, and then I have 5/2 NK from the 3/2 NK for the internal energy plus this 1, which was also times NK, so that gets me to 5/2. Okay. If I take that, I can do a little bit more stuff to that. So in the next line down here, we've labeled the entropy as the translational entropy, and we've changed it to a molar quantity. Right, the M is for molar. When we do that, that means that N, the number of particles, becomes Avogadro's number, and Avogadro's number times Boltzmann's constant is R. Right, another way to think about that is Boltzmann's constant is R, the gas constant, but in terms of a single molecule instead of a mole. Right. So now I have R times the natural log of the partition function piece becomes this, where that just says we've put in the expression we usually use. Okay. And then out here, I've got 5/2 R because I had 5/2 N times Boltzmann's constant. And again, I set N there equal to 1 mole. So I get to do that, right? You'll notice I left an N in here, but that's because I want to actually do another bit of juggling with that one. And so that's why that one was left as N, because then I'm going to take the V over N piece and use the gas law to replace that with this term here. Okay. In that last line on the bottom, I've also pulled the 5/2 R from outside of the logarithm brackets and into the inside, right? So if I pull that inside, I get e to the 5/2, and that's what gives me the same expression as above, right? Because I've got the R is out in front here. And so if you're not immediately convinced of that, take a moment and just remember how to juggle your exponents and logarithms, and you should be able to make sense of that and see that you get from that one line, the second line from the bottom to the last line when you take that term inside, okay? So we get to this equation. This equation has a name. This equation is called the Sacchar tetrode equation. And so the version here is for a monatomic gas because we did only the translational part of the partition function, right? We left out any contributions from vibration and rotation, okay? We could also find a version of this equation, an expression that would work similarly for molecules with structure, where I would have to include the vibrational and rotational pieces of the partition function. It would just be a more complex equation. It would have other terms in it, okay? From these equations, I get to say this sort of thing that I've been saying a bunch, which says these let us calculate, in this case, the entropy at any temperature from what are really spectroscopic data, right? Things that get us those partition functions, right? We don't really have any spectroscopic constants persisting in here. We sort of use them in developing the partition function idea, or we would be using some spectroscopic data, I guess, if we had vibrational and rotational pieces, right? For the case of the monatomic gas, so you'll just look at the equation, you can tell the only parameter of the gas that's in that equation is the mass, m, which is there as the mass of a molecule of the gas. Okay, so that lets us do some things and calculate some entropies. What I want to do is think about how we think about entropy traditionally and how we measure entropy traditionally or calorimetrically versus this alternative pathway we've just cooked up to get the entropy statistically. right? So if you think back to general chemistry or other places where you've encountered thermodynamics, the third law of thermodynamics says the entropy of a pure, perfect crystal of any substance goes to 0 at 0 Kelvin, right? That's a reasonable statement of the third law as usually expressed. We use that when we find entropy values, right? So if we want to know the entropy at some temperature T, the entropy is always the integral of dq over T, which we can write there as the integral of Cp times dt over T. And if we took that and actually could do the measurement where we take something and we start as close as we can get to absolute 0, and we measure calorimetrically the heat flow into the substance as we take it up to some temperature, we have to account for the heat associated with any phase transitions along the way. But if we do that, we would get an entropy value. And again, if you think back to doing thermal problems in Gen Chem, you often look up things in a table and you get the standard molar entropy of something, right? Which is its absolute entropy at atmospheric pressure and room temperature. Those values are obtained by doing this measurement, typically by just doing the calorimetric measurement. Again, you start as close to absolute 0 as you can. If you're being really good at it, you extrapolate backwards a little bit by assuming the heat capacity for that last piece is similar to what it is as you go up from there, and you get a value, okay? And those values are frequently used. They're widely tabulated. They're, in general, good values. Okay. Now we have an alternative way to do this. We can do the statistical calculation for using the equation that we just derived, or the more complicated version that would include vibration or rotational motion. Wrong way. So if we do this, this is a table that lists comparisons between these things. In the various substances in the first column, the middle column has the calorimetric entropy. Think of that as the experimentally measured entropy. And then we've got values for the statistical entropies over there on the far side. And you can see that most of these are very, very close. If you look down at the bottom of the table includes carbon monoxide, CO, which is the only molecule in this set that has a structure to it, right? Meaning that it, among other things, will have an orientation to it. And that one is the one where there's the biggest difference between the two values, right? The calorimetric measurement and the statistical calculation. Now, the measurement difference still is not enormous, right? Most calculations would do fine if we used either of those values. If we're being very careful, though, we would want to know which one of these is actually the, in some sense, more correct way of thinking about it. If we had more entries in our table there, we would see that this sort of discrepancy, like in the CO entry there, generally happens for things that are polar or asymmetric molecules, right? So anything that I've got identifiable ends of the molecule, say in the case of a diatomic, in general, that's going to lead us to having some discrepancy between these two values. And we can rationalize that actually in a way that goes back to the idea when you first learn about entropy, at least in a chemistry class, we always talk about this idea that entropy is a measure of the disorder on the molecular scale, right? And that if I got to 0 entropy, that should mean that my molecules were in the most organized state possible, right? That everything was in its proper place and aligned to the maximum extent it could be, right? If I have a crystal of solid CO, and this is just a little cartoon rendering of it here using some sort of cartoon CO molecules, right? But in those pictures, imagine the gray ends are the carbons and the red ends are the oxygens. As my crystal freezes, the molecules are going to get organized so that each molecule is at a lattice position for the most part, right? If I'm cooling slowly, I'm going to get them to do that. In principle, if I was to try to put together the most organized possible version of this crystal, there should be some sort of regular pattern to the orientation of the molecules, right? Meaning maybe I would want to have all the carbons on the left-hand side and all the oxygens on the right-hand side, or what have you. What really happens if you are cooling this stuff off and getting it into the crystal is, as it crystallizes, it doesn't get a chance to do that, because as it approaches being locked in the solid, things basically get trapped in whatever position they're in. Okay, the ability to flip the molecule around end for end is lost before the thing really gets down to that minimum entropy. Once it's solidified, you don't have enough movement to be able to easily rotate those things around. Okay. What does this mean? It means that the difference between these things, the fact that if I flip back again, you'll notice that the StatMech prediction says that the entropy at room temperature for CO should be a little bit higher than the measured value says, right? And this is why, because when you do the experiment, you never really get all the way to the most organized state, because your very cold crystal you're starting off with still has this so-called residual entropy, where your molecules are not all oriented to the maximum extent possible, okay? In the case of CO, because I have just two ends to my molecule, right? There's basically, if I say this is the crystal structure, there's two ways I can put in each molecule. It's either carbon on the left or carbon on the right, let's say, as we're looking at them in the picture, okay? That means that for n molecules, there are 2 to the n possible ways you could arrange those molecules, right? And if all of those are represented in a sample, then that gives us a residual entropy. And that entropy turns out to be equal to R times the natural log of 2, where the 2 here, this 2, comes directly from the fact that there are 2 orientations, right? And that says that because I have only 2 possible ways to sit the molecule in there. If I calculate that, that predicts a difference of about 5.8 joules per Kelvin per mole. If I flip back to my data here, my data have a difference of about 4.6 joules per Kelvin per mole, right? So the difference is not quite as much as this might predict. What that says is that the orientation probably is not entirely random, that in some little pockets things actually get themselves oriented more and less well, but that some of this does survive. And that happens reproducibly for a variety of different molecules, right? So it's a case where this somewhat abstract calculation, in a way, can get us a better value than what we can obtain experimentally, just because of inherent limits of not being able to get the correct zero entropy state or to produce that experimentally. Is it the most important thing in the world? No, it's really not. But it's sort of a nice curiosity, and at least for me, the idea that it kind of confirms that a lot of these things we've been doing do coincide with physically measurable things is comforting at the end of what's been a pretty mathematical stretch of work here, right? All this work with the various partition function expressions and whatnot. All right, that concludes module 6. I guess this one is on statistical mechanics. The course now will move in a rather different direction when you come back in for the next videos. Thanks.